Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll dive deep into mastering Amazon ElastiCache for Memcached. You'll learn how Memcached fits into modern architectures as a high-performance, in-memory key-value store, and explore its core capabilities, scaling strategies, and best practices for deployment on AWS. Let's get started. Amazon ElastiCache is a fully managed, low-latency, in-memory data store and caching service that supports two popular open-source engines, Redis and Memcached. It is purpose-built to power high-throughput, real-time applications by reducing data access latency to microseconds and enabling applications to scale seamlessly with minimal operational overhead. At its core, ElastiCache allows you to offload frequently accessed or transient data from slower backend data stores, such as relational or NoSQL databases. This improves overall application performance and reduces load on primary databases, often resulting in significant cost savings. Whether you're dealing with high-volume transactional systems, low-latency microservices, or event-driven architectures, ElastiCache can act as a vital acceleration layer. For Redis, ElastiCache offers advanced capabilities such as cluster mode for horizontal partitioning, read replicas for scaling read throughput, and multi-AZ with automatic failover for high availability. It also provides daily backups, point-in-time recovery, and encryption in transit and at rest to meet enterprise-grade security and compliance requirements. For Memcached users, ElastiCache delivers a simple, high-speed caching layer with a multi-threaded architecture and automatic node discovery. ElastiCache is ideal for a wide range of use cases, such as session management, real-time analytics, leaderboards, API response caching, and pub/sub messaging systems. Its flexibility, performance, and seamless integration make it a foundational component for building modern, cloud-native applications that demand speed, scalability, and reliability. Amazon ElastiCache for Memcached is a fully managed in-memory key-value store designed to deliver ultra-fast data access for applications that demand low-latency responses. By serving frequently accessed data directly from memory rather than relying on disk-based databases or storage systems, ElastiCache dramatically reduces response times and improves application throughput. At its core, Memcached is a simple, lightweight, and high-performance caching engine. It is purely volatile, meaning it does not support data persistence, replication, or automatic failover. When a node restarts or experiences a failure, all data in memory is lost. While this may initially seem like a drawback, it's actually a deliberate architectural choice that benefits specific use cases. For scenarios where cached data is easily regenerable, such as pre-rendered pages, API responses, or database query results, this volatility is acceptable and even beneficial, allowing the system to operate with reduced complexity and overhead. Memcached follows a multi-threaded and event-driven model, enabling it to efficiently manage thousands of simultaneous connections. This makes it a robust solution for high-throughput environments like real-time applications or large-scale web services. It is designed for horizontal scalability, where each node functions independently without inter-node communication. This stateless design allows easy scaling by simply adding more nodes. Key distribution, or sharding, is handled on the client side, usually via consistent hashing, ensuring even load distribution and minimizing cache misses during scaling events. A standout feature of Memcached is its ability to handle relatively large data objects. While the default object size limit is 1 MB, it can be configured to support up to 512 MB per item, making it well-suited for storing complex, serialized objects, pre-rendered HTML fragments, or lookup tables. ElastiCache for Memcached is particularly well-suited for cache-aside patterns, where the application controls when to load or invalidate data in the cache. It's a great fit for non-critical ephemeral data caching scenarios, such as storing session state, frequent database reads, user preferences, or temporary computation results. Amazon ElastiCache for Memcached is an excellent choice when simplicity, blazing fast access times, and horizontal scalability are critical, allowing developers to offload pressure from backend systems, reduce latency, and optimize the performance of modern cloud-native applications. The architecture of ElastiCache for Memcached is designed for simplicity, speed, and scalability. At its core, Memcached follows a shared nothing node-based design. Each node operates independently with its own allocated memory, CPU resources, and network stack. There is no coordination or data sharing between nodes, which minimizes overhead and supports low latency performance at scale. Memcache does not support replication or automatic failover. If a node fails, the data stored on it is lost, and the application must refetch and repopulate it. While this might seem like a trade-off, it actually makes Memcached a perfect fit for scenarios where data can be regenerated quickly and high availability is not mission-critical at the cache layer. A defining feature of Memcached architecture is its reliance on client-side sharding. Instead of the service itself managing how data is partitioned across nodes, Memcached clients are responsible for determining where to read from or write to, often using consistent hashing. This allows applications to distribute keys across multiple nodes efficiently and facilitates horizontal scaling simply by adding new nodes to the cluster. Each Memcached node runs a multi-threaded server process, capable of handling large numbers of concurrent connections. This design ensures that Memcached can support high throughput and low latency access even under demanding workloads. Another architectural characteristic is that Memcached has no persistence layer. All data is held in RAM and is lost upon node termination or restart. This ephemeral nature of the cache is consistent with its intended use to temporarily offload frequently accessed data from backend systems. While this architecture delivers simplicity and speed, it places the responsibility of managing availability, consistency, and failover on the application layer. It's best suited for stateless, high-volume use cases like session management, metadata caching, and dynamic page rendering. In this deployment view, we see an Amazon ElastiCache for Memcached cluster deployed within a private subnet that spans across 3 availability zones, AZs, for enhanced fault tolerance and availability. The cluster consists of 4 Memcached nodes, evenly distributed across the AZs to support horizontal scaling and high availability of cached data. While Memcached itself does not support replication or failover, spreading nodes across multiple AZs helps mitigate the impact of an AZ failure on overall cache availability. Access to the Memcached cluster is managed through an EC2 instance located in a public subnet within the same virtual private cloud, VPC. This EC2 instance serves as a client application that connects to the Memcached nodes. To enable secure communication, security group inbound rules are configured to allow traffic from the EC2 instance's subnet to reach the Memcached nodes. These rules enforce controlled access and ensure that only trusted resources within the VPC can communicate with the cluster. The Memcached cluster operates in a private subnet to reduce exposure to the public internet and strengthen security posture. The EC2 client in the public subnet acts as a bridge, potentially running an application tier or a bastion host that can securely connect to the private resources. This deployment pattern is common for scenarios where caching is used to reduce database load and accelerate dynamic web applications. Memcached auto-discovery in Amazon ElastiCache is a powerful feature that simplifies the operational complexity of maintaining distributed caching layers. In traditional deployments, clients connecting to a Memcached cluster had to maintain a hard-coded list of cache node endpoints. Every time a node was added, replaced, or removed, such as during scaling operations or node failures, this list would need to be manually updated, often requiring application redeployments or restarts. This manual process was not only error-prone, but also disrupted availability and introduced the risk of cache inconsistencies. Auto-discovery solves this challenge by introducing a dynamic and automated mechanism for maintaining the cache topology on the client side. With auto-discovery, the client connects to a single configuration endpoint provided by ElastiCache. This is not a cache-serving endpoint, but a control plane interface. When contacted, the configuration endpoint returns metadata about the cluster, including the IP addresses and status of all cache nodes. Enhanced Memcached client libraries, such as the ElastiCache Java client, can use this metadata to automatically populate and refresh their internal list of active nodes. This capability is especially valuable during cluster changes. When nodes are added or removed during horizontal scaling events, or when a node is replaced after failure, the client library seamlessly updates its routing configuration without any human intervention or service interruption. Under the hood, clients continue to use client-side sharding, typically implemented using consistent hashing, to determine how keys are distributed across the current set of nodes. This means that even as the cluster topology changes, data remains evenly distributed, cache hit rates stay optimized, and the application continues to operate smoothly. Auto-discovery also plays a crucial role in resiliency and elasticity. For applications with high throughput or those deployed in a stateless microservices architecture, it ensures that the caching layer is always in sync with the backend infrastructure. The automatic adaptation to topology changes means faster recovery from failures and frictionless scaling during traffic surges. It's important to note that auto-discovery is a feature specific to Memcached in ElastiCache. Redis, which uses a different architecture and discovery model, does not support this particular behavior. When it comes to the incredible speed and efficiency of Memcached, one of the key mechanisms working behind the scenes is slab allocation. Instead of allocating memory dynamically each time new data is stored, Memcached takes a proactive approach. At startup, it divides all available memory into large fixed-size blocks, called slabs. Each slab is further organized into slab classes, where each class holds chunks of a specific size range, say, chunks of 64 bytes, 128 bytes, 256 bytes, and so on. When a new object needs to be cached, Memcached doesn't waste time hunting for space. It quickly places the object into the best-fitting slab class based on the object's size. This method almost completely eliminates external fragmentation, where memory would otherwise get scattered and wasted over time. It keeps memory usage predictable, compact, and fast, even under heavy and unpredictable workloads. Slab allocation introduces a small amount of internal fragmentation, but given how fast memory operations become, this trade-off is well worth it. Over time, some slab classes might fill up faster than others, depending on how your application's data evolves. This is where slab rebalancing comes into play. Memcached can intelligently reassign slabs from slab classes with low usage to those experiencing high demand, allowing the system to adapt on the fly without restarting or significant downtime. When memory is exhausted, Memcached doesn't crash or slow down. It simply starts evicting items. It follows a least recently used LRU strategy within each slab class, meaning that the least recently accessed items are the first to be removed. This ensures that only the most valuable and recently used data remains cached, keeping your application performance sharp. Finally, this slab-based approach allows Memcached to operate with minimal locking and high concurrency, which is why it performs exceptionally well under thousands of simultaneous client requests. When optimizing Memcached for performance and memory efficiency, one of the key techniques to understand is chunk size tuning. At the heart of this is the growth factor, a parameter that controls how slab classes increase in size. By default, Memcached uses a growth factor of around 1.25, meaning each slab class is 1.25 times larger than the previous one. Adjusting this number can have a dramatic impact on how well memory is utilized. If you raise the growth factor above 1.25, the system creates fewer larger slab classes. This approach reduces CPU overhead with fewer slab classes to manage. However, the trade-off is decreased memory efficiency, with more wasted space due to larger chunk sizes not matching object sizes exactly. On the other hand, setting the growth factor below 1.25 creates more slab classes with smaller differences between them. This tighter fit improves memory usage, but at the cost of higher CPU overhead, since managing many slab classes becomes computationally heavier. Before you even think about adjusting the growth factor, it's critical to profile your data size distribution. Look closely at the objects your application is caching. Real-world testing has revealed interesting trends. Web applications caching small session data tend to perform best with a growth factor around 1.15 to 1.20. In contrast, larger, mixed-content workloads, like those serving media files or JSON payloads, may benefit from slightly larger growth factors, around 1.30, achieving better throughput without majorly impacting cache hit rates. Finally, Memcached allows for custom slab configurations through parameter groups in ElastiCache. Overriding the default settings becomes essential when you observe consistent slab evictions for specific object sizes. For example, applications dealing with uniform telemetry data or fixed-size tokens can benefit enormously from tailored slab sizes. Knowing when and how to adjust these settings can lead to major improvements in cache efficiency and application responsiveness. Let's dive into how Memcached handles memory management and eviction strategies, specifically focusing on the least recently used LRU algorithm. Memcached uses LRU to evict the least recently accessed items from memory when a slab class runs out of space. Each slab class maintains its own LRU queue independently, ensuring that eviction is handled in a way that minimizes the impact on the system. Monitoring the eviction rates by slab class is a crucial practice for ensuring optimal performance. By keeping an eye on these rates, you can identify when memory is being overutilized or when inefficient eviction patterns are emerging. This helps in making informed decisions to improve cache efficiency and overall system responsiveness. Another key point to consider is the use of time to live (TTL) values. Setting appropriate TTL values based on your application's access patterns ensures that memory is freed up quickly when it's no longer needed. By assigning TTL thoughtfully, you can optimize the use of available memory and prevent your cache from becoming overloaded with stale data. To further improve your cache hit ratios, consider implementing application-level pre-invalidation. This strategy allows you to proactively remove data that you know will no longer be needed, particularly for critical data sets. It helps reduce unnecessary cache misses and ensures that your application performs efficiently. Lastly, it's important to be aware of the concept of slab calcification. This happens when a slab becomes filled with infrequently accessed or expired objects, which can lead to inefficient memory usage. Recognizing this pattern and addressing it promptly can help maintain your cache's health and performance over time. Scaling ElastiCache for Memcached is a straightforward yet powerful mechanism thanks to its stateless, distributed nature. Memcached supports horizontal scaling, which means that capacity and throughput can be increased simply by adding more nodes to the cluster. Each node operates independently. There's no coordination or shared state between them, which makes it ideal for use cases where speed and simplicity are paramount. It's important to note that Memcached does not support replication or failover. Each node is a standalone cache server. If a node fails or is terminated, its data is lost. Applications relying on Memcached must be designed to repopulate the cache quickly and gracefully. Scaling in Memcached is handled via client-side sharding. Clients, typically using a consistent hashing algorithm, determine which node is responsible for storing a particular key. This design makes the system highly scalable, but it also means that when nodes are added or removed, the mapping of keys to nodes changes. Consequently, previously cached data may become inaccessible, leading to a drop in the cache hit ratio until the cache is repopulated or warmed with active data again. ElastiCache for Memcached does not perform automatic data rebalancing when the cluster size changes. It's up to the application logic or enhanced Memcached client libraries to handle these transitions smoothly. Fortunately, Memcached auto-discovery feature simplifies this process by allowing clients to dynamically retrieve the updated node list from a configuration endpoint. This makes it easier to handle changes without restarting or redeploying the application. One important architectural limitation of ElastiCache for Memcached is that vertical scaling is not supported. This means you cannot simply increase the CPU or memory capacity of an existing cache node. There's no option to upgrade the instance type in place, as you might with an EC2 instance or a database. So when your application outgrows the memory or compute capacity of the current instance type, for example, if you're running into high eviction rates due to memory pressure or latency due to CPU bottlenecks, the recommended approach is to provision a new Memcached cluster using larger instance types. Since Memcached is often used for non-persistent transient data, this migration strategy is generally acceptable and low risk, especially for use cases like session caching, query results, or page fragment storage. While Memcached lack of vertical scaling may seem limiting at first, It aligns with its design philosophy of simplicity, speed, and statelessness. With the right strategies in place, such as proactive monitoring and graceful cutover processes, you can still scale effectively to meet growing application demands. Intelligent caching patterns and performance optimizations are critical to ensuring that your Memcached setup operates efficiently under varying workloads. One critical approach is using staggered expiration times to prevent thundering herd problems. It's important to understand the trade-off between two common caching strategies, write-through and lazy loading. Write-through caching ensures that data is written to the cache and the underlying data store simultaneously, while lazy loading only updates the cache when data is requested. Each approach has its pros and cons depending on your specific use case, and striking the right balance is key to optimizing performance. A two-tier caching strategy, where you separate hot and warm data, can also improve efficiency. Hot data is accessed frequently and should be stored in faster, more expensive memory, while warm data, accessed less often, can reside in slower, more cost-effective storage. This helps to optimize memory utilization and cost. To reduce cache misses, consider using Bloom filters. These probabilistic data structures can help you quickly determine whether a cache miss is likely before actually querying the cache, reducing unnecessary operations. When it comes to configuration, synthetic benchmarking tools are essential for simulating realistic workloads. Tools like Memtier Benchmark allow you to fine-tune your cache settings by testing them against various traffic patterns. Shadow traffic testing approaches can also help you simulate production loads without impacting actual users. Implementing a canary deployment strategy for cache configuration changes can minimize risk by allowing you to gradually roll out updates and monitor the impact on system performance. Understanding key performance metrics and their correlation is crucial for maintaining an optimized caching system. For example, a higher hit ratio often correlates with better throughput, but it's essential to monitor the trade-offs between memory utilization and latency. Additionally, CPU utilization can vary depending on the types of operations being performed, so it's important to align these metrics with your specific performance goals. We'll now explore how Amazon ElastiCache for Memcached integrates seamlessly with other services in the AWS ecosystem to optimize performance and scalability. First, let's look at AWS Lambda integration patterns. Memcached works perfectly with Lambda to speed up serverless applications. By leveraging Memcached as a caching layer, Lambda functions can quickly fetch and store data in memory, reducing the need for expensive calls to slower data sources. This is particularly useful when your Lambda functions are triggered frequently and need fast access to commonly used data. With this integration, you can also set up automatic cache invalidation when data changes, ensuring that your cache remains up to date in real time. Next, container-based application architecture benefits from ElastiCache for Memcached as well. Whether you're using ECS or EKS, Memcache can serve as a shared caching layer, improving performance across microservices and containerized applications. By providing quick access to frequently used data, Memcached reduces the load on backend services and improves response times. This is ideal for containerized applications where performance and scalability are paramount, enabling you to scale your cache layer alongside your containerized services for optimal efficiency. Another important integration is with API Gateway. Memcached can be used to cache API responses, dramatically reducing the need to repeatedly query backend services. When integrated with API Gateway, Memcached speeds up the response time for commonly accessed API calls, reducing the load on your backend and ensuring better overall performance. This integration is especially useful in high-traffic environments where caching frequently accessed data can significantly improve API scalability and reduce latency. These integrations help make Memcached a powerful tool in the AWS ecosystem, enhancing the speed and scalability of your applications. Monitoring Amazon ElastiCache for Redis through Amazon CloudWatch provides comprehensive visibility into the health, performance, and behavior of your Redis clusters. CloudWatch surfaces a wide range of key performance indicators, such as CPU utilization, freeable memory, network bytes in and out, and connection counts. These metrics help teams proactively identify signs of performance degradation or capacity saturation. In addition to general system-level metrics, CloudWatch offers Memcache-specific insights, like bytes used for cache, tracks how much memory is currently occupied by cached items. Command get and command set provide counts of read and write operations. Bytes read from network and bytes written to network provide insight into network throughput, and get hits and get misses to calculate the cache hit ratio. These are crucial for evaluating cache effectiveness and the health of replication processes, especially in multi-node or highly available configurations. To support proactive monitoring, CloudWatch alarms can be configured to trigger notifications or initiate automation workflows when specific thresholds are breached. For example, when replication lag exceeds acceptable limits or memory usage approaches capacity. This ensures that issues are addressed quickly, reducing the likelihood of outages or degraded user experience. ElastiCache supports both basic, 5-minute, and detailed, 1-minute monitoring intervals. Choosing detailed monitoring allows for finer granularity, which is particularly useful in identifying intermittent or short-lived spikes in system load. CloudWatch metrics also provide guidance for scaling decisions. Persistent trends in high memory usage, CPU pressure, or increased evictions can indicate the need for vertical scaling, larger instance types, or horizontal scaling, more shards in cluster mode enabled. Finally, CloudWatch integrates seamlessly with other AWS monitoring and automation tools. For instance, teams can combine metrics with AWS CloudTrail logs for auditing, AWS X-Ray for tracing end-to-end service interactions, or AWS Lambda to automate responses to certain conditions. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.